Hi everybody, today is May 26th and we are starting a new unit, and I walked around my house and looked for some items that we would be studying in this unit. I've got some bleach, baking soda, soap, lemon juice, vinegar, aspirin, limes, an orange. All of these things are either acids or bases. And this is our new unit. And we're going to first start off looking at the properties of acids and bases. So as you can see here, I've divided that up. Acids that are edible tend to taste sour or tart. They are electrolytes, which means they ionize or dissociate in water. We'll talk about that shortly. They are described in terms of pH, which describes their concentration, and range from 0 to 6.9. Acids are corrosive. They react with and destroy metals, and they often form hydrogen gas when they react with metals. On the other hand, bases tend to taste bitter if they are edible. They are also electrolytes like acids, but their pH range is from 7.1 to 14, and bases tend to have a slippery feeling. So let's begin talking a little bit about pH. pH describes the concentration of acids and bases, and it represents the power of hydrogen. And the pH scale is based on pure water or distilled water. So a few characteristics of water that we need to be aware of. First of all, water self-ionizes. So if I had pure water in a container, it wouldn't just exist as H2O. You'll see we have equilibrium because we have a double-headed arrow here, and this water always self-ionizes. It kind of breaks apart into hydrogen ions and hydroxide ions. Or we could represent the same thing, the same self-ionization, as water ionizes into hydronium ions and hydroxide ions. And I want to take this opportunity to remind you all that these polyatomic ions are represented in table E. Here's that hydronium ion. Here's that hydroxide ion, okay? Now let's talk about that hydrogen ion. It can be called the proton as well. So a quick review of the atomic structure of a hydrogen atom. A neutral hydrogen atom can be represented this way, a simple Bohr diagram, right? The nucleus only contains one proton. There's no neutrons, by the way, in hydrogen. It's that small. And that hydrogen atom only has one electron in its first energy level. So it's a neutral atom because the positives equal the negatives. Now, when the hydrogen atom loses that electron, all that's left to it is the hydrogen ion, which is really just a proton. So don't let it throw you. Sometimes in acid-base lessons, we'll talk about that proton. It has a +1 charge. That is all that is remaining of that hydrogen atom. And there's that electron that was given off. So in the self-ionization of water, it can form a proton or hydrogen ion, and it forms a hydroxide ion. So pure water has absolutely nothing else in it but H2O. But that water self-ionizes, and when it does, it has equal hydronium and hydroxide ions, and equal hydrogen and hydroxide ions. And that double-headed arrow represented the equilibrium between these ions. And if we add another substance to pure water, it can shift that equilibrium. And that is what's going to create an acid or a base. So you will find that bases like bleach have an excess of hydroxide ions, whereas acids like vinegar have an excess of hydrogen or hydronium ions. There's a shift in that equilibrium. So let's start looking at the pH scale. And I imagine you've learned a little bit about this in the past, but we're going to review some and we're going to add quite a bit here. So what's the range of the pH scale? The range is from 0, correct, to 14. And right in the center is pH of 7. Well, on the top part here, I'm going to talk about that hydrogen ion concentration. And by the way, you're going to see brackets. Brackets refer to concentration. So I'm not going to have to spell out that word every time. We are always looking at the relative molar concentration of hydrogen ions and hydroxide ions when we're looking at the pH scale. Because as a reminder, this is based on pure water, and pure water ionizes, self-ionizes, to generate hydrogen and hydroxide ions. And if you recall, pure water has a pH of 7. And that is where you have equal hydrogen and hydroxide ions. Let's look at these hydrogen ion concentrations. The strongest acids have the greatest amount of hydrogen ions. So you're going to find that the strongest acid would have a pH of 0. Acids and bases always have both hydrogen and hydroxide ions, but acids have a lot more hydrogen ions, whereas bases will have a lot more hydroxide ions. And the pH scale is a logarithmic scale. And when you take Algebra 2 and pre-calculus, you will be learning about logarithms. We're going to look at that at a superficial level for chemistry. And as the strongest acid has 1 times 10 to the 0 hydrogen ion concentration. Then we go here, 1 times 10 to the negative 1, 1 times 10 to the negative 2, 1 times 10 to the negative 3. You're going to find that as we move the whole number pH value, we're getting a 10-fold decrease in hydrogen ions, right? These numbers are getting smaller by 10 times each value. So here's our pH values, 1, 2, 3, 4, 5, and 6. And that would continue all the way to the end here, where you have only 1 times 10 to the negative 14 hydrogen ions here. That's a really tiny number, but they exist. So the strongest bases have hydrogen ions. It's just very, very small amount. We also want to think about these values here. What are the units that we're looking at here? We're looking at moles per liter, right? These are molar concentrations. That's 1 times 10 to the negative 3 moles per liter. Let's look at the other end, the hydroxide ion concentration. In the strongest acid with a pH of 0, it is 1 times 10 to the negative 14 hydroxide ions. They do exist in acids, but a very small amount. And again, every whole number pH increment is a 10-fold difference. So let me go to the strongest base here, which would have a pH of 14. You have 1 times 10 to the 0, which is the pH of 14. That is the hydroxide ion concentration, okay? So at this end of the scale, at a pH of 14, these are the hydrogen ion concentration, 1 times 10 to the negative 14, it's very small, relative to the 1 times 10 to the 0 hydroxide ion concentration. And we have the opposite at the opposite end. For example, let's look at this. If I have a substance with a pH of 3, that is, right here, it has 1 times 10 to the negative 3 moles of hydrogen ions per liter. Well, how many hydroxide ions does it have? Well, actually, the POH, the power of the hydroxide ions, is going to be 11. Because guess what? 11 plus 3 gives us the whole range of the pH scale, which is 14. Likewise, if I have a pH of 7, as in pure water, guess what? The POH equals 7. You have exactly equal values for the hydrogen and hydroxide, but the equilibrium shifts depending on whether you have an acid or a base. So in this example, there is a favoring of hydrogen ions here because this is an acid. There's more hydrogen ions as compared to the hydroxide ions. There's 1 times 10 to the negative 3 hydrogen ions and only 1 times 10 to the negative 11 hydroxide ions. There are 2 ways that we will define acids and bases. Arrhenius acid and base definition. And a scientist, Svante Arrhenius, came up with this definition. What it does is it explains the properties of acids and bases in the context of those hydrogen and hydronium ions relative to the hydroxide ions. Okay, so Arrhenius acids release excess hydrogen or hydronium ions in water. So let's look at these 2 examples. Hydrochloric acid, when placed in water, ionizes to become hydrogen ions and chlorine ions. This creates an excess of those hydrogen ions and therefore falls into the definition of an Arrhenius acid. Likewise, nitric acid placed in water ionizes to form more or an excess of hydrogen ions and nitrate ions there. So these are, if you note, these are molecular acids. Molecular compounds have nonmetals associated with it. And when molecular compounds get dissolved in water, they are said to ionize. Now I have another example here of a molecular acid. This is sulfuric acid. And actually, so here it is. Right, here is our sulfuric acid. This acid, when placed in water, also ionizes into hydrogen ions and this hydrogen sulfate. Well, this is a more complicated acid in the sense that there's 2 hydrogens associated with it, as opposed to the single hydrogens here. That hydrogen sulfate further can ionize, releasing another hydrogen ion, and that sulfate ion. So this is considered to be diprotic. It's a diprotic acid because it's got 2 protons to release per molecule. It's a diprotic acid. Whereas these are monoprotic acids. They only have 1 proton to release. Let's move on to Arrhenius bases. So by definition, an Arrhenius base releases excess hydroxide ions in water. So I have two examples here. Sodium hydroxide is a very strong base, actually. And it's when we place that in water, it dissociates, okay, to become sodium ions and hydroxide ions. And we have an excess of them. Calcium hydroxide placed in water dissociates into calcium ions and actually two hydroxides. This is considered dissociation because these are ionic compounds. Sodium hydroxide and calcium hydroxide. We have metals and nonmetals. And ionic compounds dissociate when they dissolve in water. Now, a quick look back. I've got my acids down here and the bases here. I wanted to mention one of the properties that we started this lesson with. That is, we described acids and bases as electrolytes. Electrolytes are substances that are capable of conducting electricity. And why are they capable of conducting electricity? It's because of all of these mobile ions. I'd like to introduce you now to tables K and L. So we have our common acids listed in table K. You'll notice that you're given the formula and the name for them. So in Regents Chemistry, you are not expected to learn the rules for naming acids and bases. So they give you these examples of how they are named and their formulas. Let's move on to our final part of this lesson, and that is neutralization is a process that occurs when an Arrhenius acid and base react to form a salt and water. We'll do this example. We're going to take our sodium hydroxide, react it with hydrochloric acid, and this is going to yield, remember these oxidation states, sodium, positive sodium is going to want to bond with negative chlorine. Positive hydrogen is going to want to bond with the negative OH. So we end up with NaCl plus HOH. What do we get here? We've got the base reacting with an acid. We create a salt. Sodium chloride is a salt. It's an ionic compound, and all ionic compounds, by the way, are salts. And here's our water. So all neutralization reactions are going to involve some acid or base interacting to form a salt and water. Do you remember the name of this type of reaction? I hope you're thinking double replacement, because you would be right. I hope you enjoyed this lesson. Have a wonderful day. Bye.